In 13.8, we're going to be computing arc length, so the length of a curve. Here we're going to first look at a vector valued function r. The formula is fairly straightforward, and it's similar to that from single variable calculus. If you look at the length, it's going to be the square root of the derivative squared of each one of the components and then add it up. So when you look at the square root of the derivative squared of each component, that's simply the derivative of r, and you're computing its magnitude. Example 1, we're supposed to find the arc length of our function r. So the first thing I'm going to do is I'm going to compute the derivative, r prime, which is simply the vector 2, comma t, comma 2t to the 1/2. Our length is going to go from 0 to 4 for the t values that are given. It's going to be the square root of 2 squared, or 4, plus t squared, plus 4t dt. Oftentimes when we're computing arc length, we end up with something under the square root that we can't really figure out by hand, so we need to use a calculator. However, this particular problem, I don't have that issue because the factored form of what's underneath the square root is t plus 2 quantity squared. So you notice the square root and the square cancel. And this is simply the integral from 0 to 4 of t plus 2 dt. And then the length would be t squared over 2 plus 2t. And we'll evaluate that from 0 to 4. Looks like it's going to be 8 plus 8 and then minus 0. And our arc length is 16. Whenever we work with vector valued functions, we have to be clear on what is a vector answer and what is a function answer. Going back up to the top, something to note is when we figure out arc length, it's not a vector. Let's go on to the other page and look at another example. So we want to find the speed of the trajectory for r from t is equal to 0 to natural log of 3, and then we're going to find the arc length. So when we talk about the speed of our trajectory, can't speak of course, remember speed is the magnitude of the velocity, which is simply the derivative of r, find its magnitude. For the first part of this question, I'm going to compute the derivative, r prime, and then the derivative of e to the t times sine of t. Remember, I'm going to have to use the product rule. So that'll be e to the t sine t plus e to the t cosine t. Second component is e to the t cosine t minus e to the t sine t. And then the last component is just e to the t. So that would be my derivative. And if you want, you can go ahead and factor out e to the t from each component. I think it might be nicer when I compute the magnitude to write this as e to the t in parentheses sine plus cosine. and then e to the t, cosine minus sine. Computing the magnitude of r prime, I have the square root of e to the t squared sine t plus cosine of t squared plus e to the t squared cosine of t minus sine of t squared plus e to the t squared, all underneath this square root. So I could factor out an e to the t, and it's squared, so that can come out as just e to the t in front of my square root. And then looking at what remains, sine t plus cosine t squared is simply sine squared plus 2 sine cosine plus cosine squared plus cosine minus sine squared is going to give me cosine squared minus 2 sine cosine plus sine squared, and then plus 1, because I factored out the e to the t squared. I can see that I have a plus 2 sine cosine minus 2 sine cosine that will cancel. And then looking at what's left over, I have 2 sine squared plus 2 cosine squared plus 1. And then the 2 sine squared, 2 cosine squared. If I factor out the 2 sine squared plus cosine squared, it's just 1. And I have e to the t. This becomes the square root of 3. So that's the speed at any t value between 0 and natural log of 3. So if we were to talk about the speed and look at the speed from 0 to natural log of 3, what that gives you is at 0, e to the 0 times square root of 3 is just square root of 3. So the speed ranges from the square root of 3 to 3 square root of 3. As t goes from 0 to natural log of 3. So this is how our speed varies. Now the next part of this question was to find the arc length. Remember, I'm going from 0 to natural log of 3. But we already found the magnitude of the derivative of r, so remember that was just the square root of 3 times e to the t. So I'm ready to integrate square root of 3, e to the t, evaluating from 0 to natural log of 3. That'll be 3 square root of 3 minus square root of 3, or 2 times the square root of 3. So that would be our arc length. The next thing we're going to do is we're going to look at the arc length of a polar curve. And it's pretty simple. If you have your function r written as a function of theta, to figure out the arc length, it's simply the square root of r squared plus r prime squared. In example 1, we're supposed to find the length of the complete curve, r equal to 1 minus cosine of theta. So when I'm looking at the complete curve, I have to know my theta values. If I were to sketch a graph, this looks like a heart. Something like that. We'll pretend like it's symmetrical. It's going to start when theta is equal to 0, and then we go around. Notice that there is symmetry, so I could stop at theta equal to pi if I choose to, and then compute the arc length as 2 times the integral from 0 to pi. Or you could simply integrate from 0 to 2 pi. And then we're looking at the square root of 1 minus cosine of theta squared, plus the derivative is sine, so plus sine of theta squared d theta. I'm going to have to multiply this out underneath the square root to get 1 minus 2 cosine of theta plus cosine squared theta plus sine squared theta. And d theta. So I can see that the cosine squared plus sine squared is equal to 1. So this here is 1. And then I have the integral from 0 to pi, square root of 2 minus 2 cosine theta. I could factor out a 2. It'll come out as the square root of 2. So 2 square root of 2. But you don't have to. You could leave it in. And I have 1 minus cosine of theta. Unfortunately, I don't know how to integrate that. But what I'm going to do is I'm going to go back to my trig identities. So remember that sine squared theta is equal to 1 minus cosine of, if the argument is theta, we double it, so it's a 2 theta, divided by 2. I have a 1 minus cosine, not 1 minus cosine 2 theta. So the pattern is whatever the argument is on the sine squared, you double it. So also note that sine squared of theta over 2 will be equal to 1 minus cosine of theta over 2. So I can replace the 1 minus cosine with 2 times sine squared of theta over 2. Our integral is now 2 times the square root of 2 from 0 to pi, square root of 2 times sine squared theta over 2 d theta. And the reason why I wanted to do that is so that the square on the sine and the square root cancel. So I can bring out the square root of 2. On the outside of the integral, that's going to end up being a 4. And then the square and the square root cancel, and I simply have sine of theta over 2 d theta. Antiderivative of sine is negative cosine. This ends up being a negative cosine of theta over 2 divided by 1/2, which ends up being negative 2 cosine of theta over 2. And then I'm evaluating from 0 to pi. So we have 4 on the outside. If theta is pi, cosine of pi over 2 is 0. So this is simply 0 minus, and then cosine of 0 is 1, so minus a negative 2. And our arc length is 8. The last thing we want to talk about in this section is arc length as a parameter. So we have been using this random parameter t. Often our t value stood for time. But let's say that instead we wanted to use arc length, and here we're going to use s for arc length. This is not the position function, this is the length of an arc. We're going to use s to stand for arc length. And we're going to look at what it means for s to be the parameter for our curve. So if your curve, r of t, uses t as arc length, so the parameter is arc length, then arc length can be computed by just taking the magnitude of the velocity vector. How you check to see if your curve is parameterized by arc length and not some random variable t is you compute the magnitude of your velocity vector and you check to see if it's equal to 1. Example 4, we're supposed to determine whether the curve uses arc length as a parameter. If it doesn't, we're going to find a description that does use arc length as a parameter. So our curve here is r of t equal to negative 2t comma t. If this curve uses arc length as a parameter, then when I compute the velocity, or the magnitude of the velocity, that should be equal to 1. So I'm looking at the magnitude of the derivative of r, which would be negative 2 comma 1. That's going to be the square root of 4 plus 1, which is the square root of 5. So notice that this is not equal to 1. So not using arc length. Again, if the magnitude of the velocity vector is 1, then your curve is using arc length as its parameter. So how would I describe this curve with arc length as a parameter? Well, I'm going to use that integral that's in the box above. So arc length, I'm just going to use s, not s of t because I'm lazy. It's going to be equal to the integral. In our case, our t values go from 0 to 5, so I'm starting at 0. I'm looking at my t values. The magnitude of the velocity, I've already computed that as the square root of 5 du. So our fundamental theorem of calculus says that this is going to be the square root of 5, u evaluated from 0 to t, which is just the square root of 5 t. So remember, this was our s. Arc length is square root of 5t. To rewrite my equation in terms of arc length, all I have to do is solve this equation for t by dividing both sides by the square root of 5. And then simply replace those t values in my equation with s over the square root of 5. Going back to my equation, it's now going to be r of s, not t. And then when I replace the t value with the s over square root of 5, I get the vector negative 2s over the square root of 5, comma s over the square root of 5. So I've changed the parameter on my vector valued function from some random t to arc length. However, I also have to change my t values. Remember, my t values were going from 0 to 5. Substituting in s over the square root of 5 for t, and then solving for s by multiplying everything by the square root of 5, I now have my s values as going from 0 to 5 times the square root of 5. And I'm done reparameterizing my curve in terms of arc length. So although this is not part of the question, what does that mean? It's probably easiest to see what this means in terms of our unit circle. So here I have my unit circle. One way to describe this circle with a vector valued function is to simply use cosine of t sine of t. So that describes this curve. But remember, it's not unique. There are many different ways I can describe this curve. So is it parameterized by arc length? Well, if it is, then for any t value I put in, the length of the arc should be equal to that t value. So for example, if I let t be equal to 0, I'm at this starting point here on the graph, and the length that I've traveled so far is 0. If I let t be equal to pi over 2, I've gone to this point, and the length that I've traveled is pi over 2. So notice my t value corresponds to the length of the arc. So again, if t is equal to pi, and I'm here at pi on my unit circle, then I have traveled a total distance of pi. So the t value corresponds to the length I've traveled so far on this curve. And what if I were to change the description and say that r of t is, say, cosine of 2t sine of 2t? If I can write sine of 2t. So again, this describes the same curve. It's still the unit circle. But let's look at some t values. When t is equal to 0, we're still at 0. And my arc length is 0. What happens at pi over 2, though? If t is pi over 2, cosine is going to be pi. Cosine of pi is -1, and sine of 2 times pi over 2 becomes sine of pi, which is 0. So I'm at the point -1, 0. I've traveled a distance of pi, which does not match up to my t value. So this is not parameterized by arc length. So basically, when you parameterize by arc length, whatever t value you put in is the same as the distance you've traveled. And that's it for this section.